Hi, my name is Tom Lever. I've created this video to offer you a guide in getting darknet YOLOv4 working on your Windows 10 PC. In front of me is the paper by Alexei Bokovsky et al. That is Alexei AB et al. As well as a set of instructions that I will use if YOLOv5 comes out, and a set of instructions that I'd like to work through with you. I'm going to switch tabs here to Alexei AB's GitHub repository. As you can see here, the README was updated yesterday, and the source folder was updated today. So YOLOv4 is actively in development and is hot off the press. It seems that Alexei Bokovsky et al. Have taken over the YOLO project from P. Joseph Redmond et al., the creators of darknet and YOLO and YOLOv2 and YOLOv3. We will use this webpage later. One thing I'd like to draw your attention to before working through this set of instructions is my detailed YouTube video detecting objects and images in videos using darknet and YOLOv3 convolutional neural networks, which is centered on getting darknet working using a Linux virtual machine on a Google server and interfacing with it in Google Colaboratory, which is a Jupyter Notebook-like environment. After creating this detecting objects detailed video, I also created a video series for training custom darknet models, YOLOv3 CNNs. Again, through the Google Colaboratory interface. All right, so let's get started on these instructions. So first thing, let's download darknet master as a zipped folder from this GitHub repository from cloner download and then download zip. And then I extracted its main contents into my documents, an AI folder, a darknet folder. Here's YOLOv3. Now we're on to YOLOv4. And here is the main contents of the YOLOv4 repository. It has a lot of solution files, a lot of data files, and a lot of configuration files. All right, so now I want to open the darknet solution for YOLOv4. So this is in the main darknet YOLOv4 directory, and then under build and darknet.solution. So it's already done for me, but at this point, you're probably going to be asked to upgrade darknet.solution to your most recent Windows SDK and platform toolset. After you do that, I would recommend closing the solution, and then, and I'll explain why, let's open darknet.vcxproj, so the project file, in Notepad. So the default solution is configured to work with CUDA 10.0. I use CUDA 10.2. I already did it, so you're looking for CUDA 10.0, but we're looking to change CUDA 10.0.props to CUDA 10.2.props and change CUDA 10.0.targets to CUDA 10.2.targets. After making these edits to the project file, save and close. And now let us configure darknet to work with OpenCV and then build. So opening up the solution again, I'm going to right click and go to Project Properties. And then going step by step through the properties, I find my way to the C++ properties. And here is system variable OpenCV dir. So going to my system environment variables, I have here OpenCV dir. And it is equal to C OpenCV 4.3.0 build. Okay, now I want to go off on a little tangent. So when downloading OpenCV 4.3 or 4.2, you can navigate to the OpenCV 4.3 release on OpenCV's main webpage, and then by hitting this sources button, I think we'll start an automatic download. Or you can go to SourceForge and download this OpenCV application. If you run this application, it will spit out a folder of different OpenCV related files, also 4.3. I believe the output of this application is what you want, because I believe it's more aligned with the C OpenCV 4.3.0 build OpenCV dir variable and how it's used in the darknet solution. Another thing regarding OpenCV is possibly you might have to go into your system variable path and add C OpenCV 4.3.0 build 64-bit VC15 bin, and this folder includes OpenCV world 4.3.0D and non-D. This may be optional for the darknet solution because I didn't see explicit references to OpenCV world in darknet. However, this addition to the system path is necessary if you plan on working with OpenCV in other Visual Studio projects. Let me take you off on a little bit more of a tangent and open up my own attempt at a simple convolutional neural network called NingNet, named after Dr. Andrew Ning, who put on the awesome Coursera deep learning specialization and has a very clear, intuitive introduction to the logic of comparing a prediction tensor and an encoding tensor. Going to the properties of this particular solution and then scanning slowly. Here is OpenCV dir again, and its include subdirectory. And then here is a reference to the directory containing OpenCV world.lib. Then continuing on, under linker and additional dependencies, here's an explicit reference to OpenCV World 430D, the library. The D corresponds to debug. If you're running a release build, you want to get rid of that D. Continuing on. Under CUDA linker, here's another reference under additional dependencies to OpenCV World. All right, so that's all of the OpenCV related property additions in your own project involving OpenCV. OpenCV is, I think, the best choice, though it's a large library when using CNNs for object detection. Regarding how it's used, here is my for loop across batches and subdivisions and images in each subdivision. And here I have a call to OpenCV's imread method, which takes in a string and outputs a CV Mat object to, in this case, an unsigned car array called training image host. And I needed to include OpenCV.hpp, which I believe lives here in C OpenCV 4.3 build include OpenCV 2, and then OpenCV.hpp. And weirdly enough, I had to play around with the ordering of this inclusion relative to inclusions of other source files / header files. I think there's some interesting dynamic between the include string statement and this include OpenCV. Just that's completely empirical. Okay, so that's using OpenCV in your own project. And that justifies adding to your system variable path this reference to the directory containing OpenCV world .dll. And for darknet, definitely you want to add OpenCV dir to your system environment variables. Okay, I think since that's all in place, we're ready to build. If Visual Studio still complains about OpenCV, try restarting your computer. But let's build the release 64-bit version. It succeeded for me. I hope it does for you too. One note I would like to make here is I cannot get the 64-bit debug version building or the 32-bit debug or release versions building. If you can get the 64-bit debug version building, please, 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 please let me know. Without a debug version, I can't use breakpoints. And darknet is massive. and it's hard to follow the logic line by line. Okay, we're almost ready to run the detector and draw bounding boxes around objects in an image or a video. But before we do that, we need to download a weights file that wasn't provided in this GitHub repository and make a few revisions to a configuration file. So the weights file is YOLOv4.weights, and you can search the GitHub repository for YOLOv4.weights. And here is a Google Drive that you can access and then download that weights file. And that weights file goes in your main darknet YOLOv4 directory. So the weights file is the product of training the darknet YOLOv4 model on the Cocoa dataset with, I believe, 80 classes. And it is used with YOLOv4, the configuration file, as well as the Cocoa data file, to draw bounding boxes around objects similar to objects in the Cocoa dataset, like dogs, trucks, bicycles, potted plants, not trash cans. So we've downloaded our weights file. Now we need to make a few edits to our YOLOv4 configuration file. So navigating to darknet YOLOv4 main directory, configuration subfolder. Then we have YOLOv4.cfg. Here it's loaded in Visual Studio Code. I've commented out the training section, which involves inputting batches of 64 images each. And each batch has 8 subdivisions of 8 images each in this case. I commented out and wrote in a testing set of configuration parameters. We're passing in a batch of 1 image with 1 subdivision with 1 image. So basically, we're forward propagating 1 image through the YOLOv4 convolutional neural network. The 3 detection layers predict the presence and class and position and size of objects. There's a coarse detection layer for large objects, a medium detection layer for medium objects, and a fine detection layer for fine objects. Basically, the detection layers work by generating a prediction tensor, comparing that to an encoding tensor, and then predicting an objectness score, a class score, and position and size. I'll get a little more into that when we discuss training your own model CNN on your own custom data set. Okay, now we're ready to actually execute a command to use the YOLOv4 weights file and the YOLOv4 model to draw bounding boxes around objects in the classic YOLO image of a dog, a bicycle, a truck, and a trash can, which is labeled as a potted plant. So I'm going to navigate to the main darknet YOLOv4 folder, press Shift, right click, and open PowerShell, and then execute the following darknet executable. The detector module within that executable, I'm specifying that we're drawing bounding boxes as opposed to training the network. I pass in a reference to obj.data and the configuration file that we edited, the weights file we downloaded from the Google Drive linked to the GitHub repository, and a reference to that classic image. Here the model is being initialized, and there's a loaded image of the dog, the bicycle, the truck, and the potted trash can. All right, so I hope this has been really helpful for you getting YOLOv4 up and running on your Windows 10 PC, maybe your Linux machine as well. Maybe Google Collaboratory even. For a Google Collaboratory tutorial, again, see my YOLOv3 videos. I hope those videos might also be helpful if you're building darknet on Linux. Again, if you can get the YOLOv4 debug 64-bit versions building, please, please, please let me know in the comments. Thanks for watching.